So I want to take some time to practice doing a little problem solving with some of the principles that we have in Unit 6. We're looking at the continuity equation. We're also looking at Poiseuille's law, or Poiseuille's law, or there's a number of different pronunciations. We might just go with P's law. So I've outlined all the equations over here. So the top one is just flow rate, and if you have a cross-sectional area, flow rate is equal to area times velocity. We have the continuity equation, A1V1 equals A2V2, where the area is the total cross-sectional area over all of the different branches you might have. Reynolds number, this is sort of just a quick little calculation to see if the flow is laminar or turbulent. Laminar flow means we can use all the rest of these equations. Turbulent flow means there's some other physics going on, and we need to pay attention to that. And then all of these lower ones are all related to P's law. So we have flow rate is equal to the change in pressure over the resistance. So this is kind of like our analog to Ohm's law in circuits. Then here's the calculation for the resistance. And here's how we can get the velocity. And this last equation isn't anything new. It's just actually a combination of really these two here and also our definition of Q being A times V. So that just is a way to go from flow rate to find out what the velocity is instead. So I want to do a couple of different examples. One of them is going to be a non-branch system. Another one I'll have as a branched system. So let's say we're in a pipe here of 2 centimeter radius, 10 centimeter length, and then it narrows to 1 centimeter radius, and then it widens back up to 2 centimeters again. And each of these segments is 10 centimeters long. And the one thing we know is that the velocity is, say, 10 meters per second going through this first region. My end question might be, well, what pressure would get the fluid through there? So we need a specific amount of pressure to actually push it through, because there's resistance here. If we don't provide enough pressure, the fluid can't even go all the way through the pipe. So what is the minimum amount of pressure we need? Or actually, I should say, what is the exact pressure we need in order to get 10 centimeter per second flow through here? So some things we might go ahead and find. We might find, well, what's the velocity in this middle region? We actually don't need to find that, but I'm going to find it anyway. We can find the velocity in this middle region, and we can guess that, it's like, well, maybe it goes up to 20 centimeters per second because the radius goes in half. Well, let's find out if that's true. So this is a continuity problem that we have to look at. So A1V1 equals A2V2. And now we can do pi R1 squared V1 equals pi R2 squared V2. The pi's will drop out here. Then we can just do the radius. And since everything's in centimeters and I'm just looking for a velocity in centimeters per second, I'm not even going to have to convert here. Later on, converting centimeters to meters will be absolutely vital if we're going to be getting pressures in terms of pascals, for instance. But here we don't have to worry about it so much. So the radius is, 2 centimeters. So we have 2 squared times the velocity of 10 equals 1 squared times the velocity of 2. Already, this square here says that we can't just say this velocity is going to go up by a factor of 2. The square is going to make it different. So V2 is going to be, so we divide a 1 over to here, so we get 2 squared times 10, so we have 4 times 10, so 40 divided by 1, so you get 40 centimeters per second. So when you have the radius, you actually quadruple the speed. Okay, great. So we know that velocity. Whether or not we actually need to know that moving forward, we've got it. So let's see what happens next. Erase this. I want to figure out the pressure that it's going to take to get through this whole system. I can actually break this up into chunks. I can say, well, what's the pressure drop through here? What's the pressure drop through there? What's the pressure drop through there? This is analogous to what we saw in circuits by having, let's say, 3 resistors. We have being a wider section, this is going to be a smaller resistance. So maybe I make a short resistor, then a longer resistor, because this is going to be a bigger resistance through here, and then a shorter resistance through that last piece. So we have some R1, R2, R3. And we're saying if we want to know what a specific current, if we were told what current we want to get through there, we'd be asking for, well, what's this delta V that can push that through there? And then we could just use delta V is equal to I times R, where we can find out what the total resistance is. We just have to add those 3 resistors in series together. So add the 3 resistors, know what the current is, and we can get what the potential is that would drive that current. Well, we can do the same thing here. We can find the resistance of each of these sections, but instead of finding delta V, we find delta P, which is, we can look at this expression here, so the flow rate times the resistance. So if I want a particular flow rate, well, I'm going to have to convert 10 centimeters per second into a flow rate, knowing the cross-sectional area, and then I can find the resistance of each of these pieces, and that's going to help me to find what total pressure difference I'm going to need, what total pressure I'm going to need, pressure gradient I'm going to need to push that through there. Okay, so the first piece we need to get is the flow rate. So we want to find this value Q. So Q is equal to the area times the velocity. So pi r squared times the velocity v. And I think I'm taking up a lot of room when I do this. So pi times the radius of the pipe, 2 centimeters. So I'm going to need this to be in meters, 0.02 meters squared. Multiplied by the velocity, also put in meters per second. So that's going to be 0.1 meters per second. And I can calculate this value. Got my handy dandy calculator. And we're going to do pi times 0.02 squared times 0.1. And I get a value of 1.26 times 10 to the minus 4 meters cubed per second. So you get a meter squared and a meter there, so we get a meter cubed per second. You'll see a previous value of Q that I put up here in a part of the video that I got rid of because I did a miscalculation. So 1.26 10 to the minus 4 meters cubed per second. All right, perfect. Have the flow rate. So now, having that flow rate, now I can find the resistance. So I need to find the resistance from each of these sections. So first we're going to do the resistance of this first 10 centimeter section. So R is equal to 8 eta L over pi r to the 4th. We get an 8. Eta, that is the viscosity of the fluid. So we'll say that this is water that's flowing through the pipe. And water has a viscosity of 0.001 pascals times seconds. So we take that value, 0.001 pascals times seconds. We'll keep all these units so we can try to see what kind of nonsense unit comes out in the end. It will not be ohms. That'd be kind of nice, wouldn't it? But, and then the length of the pipe, 10 centimeters to 0.1 meters. And then we divide by a pi r to the 4th. So the radius here, 0.02 meters to the 4th. All right, let's put some numbers in. So I have 8 times 0.001 times 0.1. If I did that already, you should be playing the home game so that you can see if you can do the same calculation, make sure that the numbers check out. If they don't, then one of us might be wrong, and I'll kind of give it a 50-50 split who that might be. I'm willing to take the blame. All right, and then divide, and I get 1591. Let's do 1592. Well, it's 1591.5. That's why I'm going to 1592. 1592. And we have pascals, seconds, meters per meter to the 4th. Well, that means pascals times seconds over meter cubed. There's probably a simplification in here. Well, this is newtons per kilogram, or we can write this as pascals, newtons per meter. Oof, that would put another meter down here, so it would be a newton times a second over meters to the 4th. The newton would be kilogram meters per second. I don't think it's anything better. I think we ought to just leave it in this unit. I believe the resistance units are pretty gnarly anyway. So 1592 is our resistance. It's going to be the same resistance in this section since it's the same length. This is basically an equal resistor over here. So R 1592 Pascal seconds per meter. So I want to find the resistance for this section of pipe as well. So being a narrower section of pipe, I'm expecting there to be a larger resistance. We can just see that in this expression, since eta and L are the same, R being less is going to make this a smaller number down here. The top divided by a smaller number gives you a bigger resistance. So if you decrease the radius by a factor of 2, then you're going to decrease this denominator by a factor of 2 to the 4th. So a factor of 16. In that sense, I should actually just be able to take this number and divide it by 16. So 1592 over 16. So I'm expecting 99.5, about 100. So let's just take a look at that quickly. If I put that number in, so 0.01, and I do the math for this. So I've got, just going back to my calculation. I said it backwards. I just said a resistance that's smaller. I want it to be bigger though. So it's 1 over 2 to the 4th. So 1 over 16 is what goes into the denominator, which means the 16 comes up top. So the resistance should be 16 times as much. So 1600 times 16. So 25,500 is what we're going to call it. About 25,500. It's 25,464. I'm going to do some rounding. Let's call this 1600. And then this is going to be 25,500, we'll call it. R equals 25,500 Pascal seconds per meter. Yeah, so 1600 times a factor of 16 gives you 25,600. That's pretty close to this value that I ended up with. Okay, so we can see that most of the pressure that we need to apply to get the fluid going through here at this flow rate of 1.26 10 to the minus 4, most of that pressure is needed to get you through this small section because there's so much resistance. So if you're going to get any particular flow rate, it's that big resistance area that you have to be pushing through. I mean, it's kind of like in the wires that it doesn't take much potential difference at all to cause current to move through, charge to move through a wire. But as soon as you put resistors in, now you got to make a big potential difference to get the current through there. All right, so we're finally at the place where we can find what is that pressure that we need. So delta P needs to be equal to flow rate times R. So Q times R total. So 1.26 10 to the minus 4 meters cubed per second. And our total, this is going to be the addition of all three of these resistance values. So we have a 1600 plus a 1600, so you get a 3200, plus this 25,500. And all of that is Pascal second per meter. I feel like we're still missing, oh no, actually this is going to be perfect. Unit-wise, meter cubed, knocks out the meter cubed. The second knocks out the second, and we're just left with pascals, which is a pressure! Woohoo! Okay, so we actually got a pressure unit out of that. That's amazing. 1.26, 10 to the minus 4, and we've got 25,500 plus 3,200, and we get some value of, curious, 3.6. 3.6 pascals. So, not too much. It's kind of it's sort of a big pipe, 2 centimeter radius, so 4 centimeter diameter. So big pipes are pretty easy to get fluid through, and 0.1 meter per second really isn't all that fast. 10 meters per second, that's just kind of like going 10 meters, 10 centimeters. 10 centimeters per second, what does that look like? 10 centimeters. Probably something like that. So the fluid's going, that's actually a pretty slow flow rate. So this is a really low pressure. It doesn't take much pressure to push it at that rate. But there you go. That gives you a sense of how we can use some of these values to determine something about our system. So the pressure needed is, let me write this over here, 3.6 pascals. I missed one equation. Let's take a look at Reynolds number. Reynolds number is going to tell us if we're, as was mentioned before, turbulent or laminar flow. So in this case, because it's such a low flow rate in kind of bigger pipes, and it doesn't take much pressure to get through there, there's a pretty good chance this is going to be laminar flow. But let's find out if that's true. So the Reynolds number goes as the density of the fluid times the velocity, the average velocity, times d over this term. And so actually the Reynolds number is going to be different in different sections of the pipe. So let's check out where it might be the highest. I think in this middle region where it's flowing the fastest is where we might expect that to be the highest. Did I determine the velocity wasn't 20? Did I calculate that was 40? I had it in my head that it was going to be 20, but I wrote it as 40. I mean, so I wrote it as 20 instead of the 40 that it actually was. Yeah, so this central region is where the viscosity, where the velocity will be the biggest. So we'll say the density of water is 1,000 kilograms per meter cubed. Let's carry the units and see what we get. Velocity is 0.4 meters per second. The d is some kind of characteristic length of the system. In the case where we have pipes, we're going to say that d is the diameter. So the diameter here is 2 centimeters, or 0.02 meters. And then the length is going to be, of course, the length of our pipe. So 10 centimeters, or 0.1. I don't know why I said that was an L. It's viscosity. Viscosity is going to be, for water, 0.001 pascals times seconds. I mean, yeah, you got a lot of pieces to keep track of. You're seeing that I make little mistakes here and there. And it's just a little bit of troubleshooting to make sure you get through these calculations the right way. So, let's just see what the number is first, and then we'll worry about the unit. 1,000 times 0.4 times 0.02 divided by 0.001. You get a value of, 8,000. Still turbulent. So the little table or in the reading, it suggested that if your Reynolds number is around 2,000 or less, when we're talking about round pipes, then we can expect the flow to be laminar. But if it's above that, then the flow is going to be considered a bit more turbulent. So I think the fact that these are such big pipes, when you have wide pipes, I mean, maybe 2 centimeters didn't sound big, but even for a water pipe, that's going to be pretty big. And at that speed, that's still fast enough that there's going to be some turbulence. Now, it's not going to be super heavy turbulence, but there is some turbulence, which means there's going to be some extra physics. There's going to be some extra losses due to the mixing and the turbulence of the water. Interestingly, if this were blood flow, of course all these numbers would be a little bit different, but let's say these were the numbers we had for blood flow. Blood is 0.004, so that actually means this whole value would be divided by 4, so your Reynolds number would be around 2,000. So if blood was moving through these pipes with all of these same values, then we actually would have just barely laminar flow. What's the unit? It's supposed to be unitless. I don't even know if I want to go through this right now. I'm going to have to take the Pascal and break it up into its parts. You want to do some unit analysis? No, you don't. You can always skip through the video to a later point if you want to, but I'm going to do this. Oh boy, yeah, a meter squared here over a meter, so it'll be a kilogram over a meter. So the meter squared and the meter cube over the meter cube just gives you a meter. You have a 1 over a second and another 1 over a second here. So it's actually 1 over a second squared. And then the Pascal is in the denominator, which is a Newton per meter in the denominator, which actually means a meter per Newton. Okay, there goes the meter. We got rid of that. I don't think we wanted to, though, because the Newton is going to have a kilogram times a meter per second squared. Pascal's is Newton per meter squared, isn't it? Here, let's leave these meters. Newton per meter squared. Okay, and now we're going to take the Newton and say that's a kilogram meter per second squared. So kilogram times meter per second squared, so that means that second squared comes up into the numerator. So the second squared and the second squared, the meter squared knocks out those meters, the kilograms knocks out those kilograms, and more unit magic. Units all gone. Reynolds number is a unitless value that tells us something about the flow. Okay. So we've sort of torn this whole system apart to see what are all the bits that we can calculate, and this gives you a sense of how we use each of these equations to calculate some things that are going on. Now what I want to do next is have a pipe that branches and think about what's going on there. So it's all the same equations and it's all the same thought processes, but we have to add that extra piece. So let's do that.